Our second speaker is Kazu Okumoto. The title of his presentation is STAR, a cloud-based innovative tool for software quality analysis. He is a well-recognized pioneer in software reliability engineering. He invented a world-famous statistical model for software reliability, the Goel model. After retiring from Nokia in 2020 as a distinguished member of the technical staff, Dr. Okumoto founded Sakura Software Solutions, which has developed a cloud-based innovative tool, STAR, for software quality assurance. Welcome.
Okay. Good afternoon. My name is Kazu Okumoto, and today I'll be talking to you about our latest tool. It's called based on the cloud-based innovative tool for software quality analysis, which is slightly different from typical topics that the machine learning or this other fancy stuff. But this is more practical, and it's actually being used. So today, what I'll do is first 10 minutes, I will go through introduction and background and a few analytics. And then we go into a live demo, show you how this tool works. Okay? And all right. I skipped the introduction since you did a wonderful job. Thank you. All right. So what is STAR? It's a software quality assurance as a service, and it integrates SaaS and automated innovative prediction analytics and the visualization of the output. So it's the forefront of digital engineering practices aimed at delivering high quality product on time. So you can make decisions based on the data-driven method and improve customer satisfaction. Okay. Now, who is using it? STAR is currently going through an extended trial with NASA. An earlier version of this tool was actually developed when I was at Nokia, and it's been thoroughly tested and customized for the largest business group in Nokia. And as far as I know, they're still using it. And what we do is we continue to advance and improve STAR for real-world applications in the field through the collaboration with experts from industry and academia. Now, as a background, I am showing you software development process diagram, and what it says is once a set of new features is identified for the release, we begin software development, starting the specification requirement specifications and software design, coding, and unit test, followed by the formal test. And there are so many different types of testing, as you might know. And some of them are integration test, feature test, system test, and stress test, stability test, and so on. So once the bulk of the features are developed and tested, we deliver to a site for customer testing, including acceptance test. And once all the features are done, all the bugs are fixed, we make the final delivery for deployment. And during the operation, certain defects are going to create system outages, unfortunately. That's what we call outages or failures. In terms of terminology, in this talk, defects, faults, bugs are interchangeably used, just to clarify, okay? So this is the software life cycle, and what metrics do we look at, right? Defects are injected throughout the entire development process, and defects, they are removed, found and removed throughout the process, throughout the cycle. So first, obviously, we need a defect count, which is shown the blue, light blue line curve. And that's what we call arrival curve, or you can say detected defects. And light brown color is the defect closure curve, or defect fixed. So we need to keep track of those two things to evaluate the quality of software. In addition, we added two more metrics related to effort data. The first one is development effort, which is the dark blue, and test effort data, which is the dark brown color. You notice those curves are not straight line, right? That means this is a dynamic behavior over time. It's not hardware, typical hardware shape. Hardware is very much straight line. So that's the difference between software and hardware. And we are looking at software creation period, okay? And the defects are detected during the test phase. So our goal is to find the defect curve, predict the defect curve during the testing. So we can make intelligent decision whether release is ready to go or not. Okay, so we'll talk more about that one, but this is the idea. So because of the shape of the curve makes this type of work a lot more challenging. Now, what's been done, current software reliability modeling, due to time of limited time, I will not go through one by one, but as I go through, I will point that out. The bottom line message here is STAR overcomes the challenges of the current software reliability models. Now, before I go to I still have 5 more minutes or so, right? Okay. I want to, highlight the analytics behind the scene. Okay, when we go to a live demo, you don't get to see this detail. So the chart on the left is a typical cumulative number of defects found over time during test period. And you notice there's a certain point where the trend significantly changed, right? In this case, 4 or 5 different points we call inflection points. We developed algorithm to find this inflection point automatically based on the exponential model, which is shown at the bottom of the page. There are 2 parameters. We use a statistical method of maximum likelihood to find the estimates of those parameters. Then as we go through, we find the inflection point. Once we find the inflection point, we move the coordinate into that point, then start over again. So we continue to repeat until the end. So in the end, we have a series of piecewise exponential models. It's not a single curve model anymore, okay? That's the difference. And in the end, last curve is the predicted curve. So as you can see, chart on the right, that's the predicted curve out of this trend analysis. And so now you can see the total defects, that's the asymptotic value. And you can also calculate residual defects, how many defects are remaining at delivery. All right, next. This is used during the planning phase. Project management wants to know what the defect curve looks like based on the plan we just set up. Okay, plan means assuming the effort data is available. And what we do is we use the previous release data to calculate the defect density over effort hour. Effort is measured in hours. Okay. So at those 2 points, D1 and D2, those are delivery dates, delivery for trial and delivery for the deployment. Now, then look at the current release. We have the effort data, so we can multiply the defect density by the effort to calculate target defect values. 2 dots you see, chart on top. And what we can do is, blue line is the effort curve. So we use the effort curve to transform, to go through those two dots. That's what we call transformation function, which is has 2 components, horizontal shift and the vertical shift. And equations are given there, relatively simple. So we have to use numerical analysis to find the optimum curve to go through those 2 dots, as close as those two dots. That's what we did. And the bottom chart, if we add actual data, you can see the validity of the curve. Okay. The third one is, how about closure curve? The input to that is the predicted arrival curve, chart on top, and current closure data. So it turns out by shifting to the right at the constant, in this case, I think 2 weeks, so it's exactly overlay, right? The perfect match. So this is typically the case we've noticed. And this is, again, part of transformation function. It's a special case. So those are the 3 things I wanted to mention. Then we can go back to the slide, begin the demo. Is there any specific questions at this point before we move to demo? Okay. This is our landing page, and we can click this demo, and here it is. We have 4 projects and a couple of releases for each. And we stay here, project A, release A. And let me begin looking at the input data. So what kind of input data? First, left-hand side, those are the dates, milestone dates, test start date, and D1 date and D2 date. And the middle section is the defect data. And if you click this download sample defect, it gives you a template. So you can copy exactly that with your data. And you can choose the file. If you click this upload defect button, it will automatically upload the data and show you what you uploaded. This is a cumulative data, exactly what you did. Okay, just to confirm your data is accurate. At the same token, system already executing. And if you go to defect trend analysis, we have several menus, sub-menus. Let's start with the executive summary. And it gives you the bottom line message. Table on the left top is the quick summary. We color coded, and thresholds are used, derived based on our experience. And this that information bar, and if you click that, gives you explanation what that means, right? D1, D2, I already mentioned. And this one is color coded red. It means at risk, yellow warning, and green acceptable, right? Now, just give you an idea, 25.8% at D1 and 12.1% D2. What does that mean? So that detailed here is in this table. So, as I said, we set the threshold 25% for red and 50% for green. And this is adjustable. If you have your own numbers, we can change that. Okay. So same way, and here's the chart. The solid line is the actual data, and dotted line is the predicted curve for arrival and closure. Looks near perfect. And look at the chart on the right, which is the different, what we call open defect, difference between the arrival and closure curve. And both look very decent, right? Now, in terms of goodness of fit, that's being used, the current practice, but we're not going to stay there. Most important things, are we predicting the right in a consistent way? So let me jump to that, what we call prediction stability. So what we're doing is, in this example, red curve, solid line, that's actual data. We use that and come up with predicted value, and we read the value at D2. That's what we're plotting at one dot here at that point. And we continue to go backwards to do the same. So you can see how the predicted value changes from week to week. And obviously, quicker it becomes stable, the better. And less variations, the better, accurate, right? That's the goal. And in this case, it's probably, we're talking about around May time frame, a couple of months before D1, it's reasonably stable. So we can tell the managers you can use it for making decisions, okay? And we have another one for decision-making purpose. If you don't like, if you like to improve quality, what else can we do as a corrective action? We chose here the 4 corrective actions. One is obviously delay the release. And second one is more testers, accelerate the arrival curve, and more developers, which is the green curve is pushed up. And the last one is reduce the content. Just to give you an idea how that works, if I say delay 3 weeks, here it is. Notice the bar is moved to the right, and the table shows you the 25.8% to 18.6 change to yellow. So that's how much you can improve, okay? And let's see one more. if I reduce the content 3%, you see the red curve, arrival curve came down because we are delivering the 3% of the content next release. So we don't count those defects. So obviously then what happened to open defects is getting close to 0 at D2, right? That's what we like to see. So we can keep trying and how best it works for you based on the cost. And reducing content means you're reducing your revenues, okay? Now, move on to 5 minutes, okay, perfect. Do we move to the second phase, which is the arrival curve prediction without actual data. Remember, we use effort data. And here is what it is. I'm going to show you. In this case, I have to use project D. And effort data looks like this. Development effort data, test effort data. And that's the previous release for project D, and project B is the current release, okay? So you can see the difference from release to release, even the same project, it makes a big difference, right? It's completely different shape and height. That's the challenges to this type of work. And RE prediction, remember that? That's two dots and curve. This is how it's implemented. And we added plus minus 10%. Okay. Now, what happens if we get more data? Data start coming in. So we continue to update the predictions based on the new data coming in. And I'm going to show you some interesting observation. We're not doing any analysis here, right? We're just showing the actual data, okay? Effort versus defect. This is both cumulative curve, remember? And both curves are highly related. I'm not going to use correlation because it's confusing. It's a static version of correlation that she was talking about earlier. That's completely different. This is, we're looking at the curve, one curve versus another. And this already gives you an idea. Blue curve is going to most likely follow the red curve, right? That's what is going to happen. But anyway, so this is how it looks like. If we have actual data up to this point, its prediction is continue to update it. And more interesting point is here. Just give me one more minute and look at this. The prediction stability starting at 0, beginning of test phase, is without actual data. We said little over 4,000 defects. And as data comes in, we continue to update this blue curve. And of course, it goes ups and downs, but within plus minus 10% limits, right? It's remarkable to me. Okay, so this thing will probably continue to go on. I don't have the data afterwards, but now you can compare this chart, all right? This one has an effort data used, all right? Compared to the defect only, the one prediction stability, okay? this is how it looks without effort data. So even the most recent data will not be able to accurately predict. Even though the goodness fit says perfect, but prediction is way off, right? Remember, we was talking about 4,000. It's not near 4,000 yet. So that's the power of having additional data, especially effort data, to predict defects. So that's my bottom line message.
Thank you, Kazu.
Thank you.